Hello, welcome to video 6 in the lecture Advanced Mathematic Modeling. In the last videos we have studied events, which are subsets of our sample space big omega, and we have seen that a probability is a function which associates every event A, a number P of A, so that P is between 0 and 1, and this P, the probability, is the likelihood that this event happens. And then we learned some rules in how we can calculate such events and deal with this. But in practice, it's very cumbersome to deal always with sets and subsets and so on. And very often we want to associate probabilities to measured events, to numbers. And so that where the random numbers come in. And so this is what I want to introduce now in this video, probabilities of random numbers. So a random number that is also a function, so that every event is associated to a number x. So we have a mapping, so that every event is mapped to the random number x of A. Since we have seen before here that every event is also mapped to a probability P of A, so by this relation we see that every number is also associated to a probability. So for every number x, by this mapping we get the probability P of x. So that's the probability that the number x appears. We call this x then also a stochastic variable. So this is a very simple concept, that we map events to numbers, and in this way we can then associate numbers to measurements or to the state variables in our models. Let's look at a simple example. Let's throw a dice 2 times. So first, if you throw the dice 2 times, so what's the sample space? So what are all possible outcomes? The sample space is the set of all tuples ij, so that I and j are natural numbers between 1 and 6. Right? I is the first dice, the outcome of the first dice. J is the outcome of the second dice. And so how many elements we have? We have 36 elements in the sample space. And now every possible subset of this could be an event. And now we do the following. So we introduce the random number, where we say that we take a tuple ij and we map this to the sum. So the sum of the 2 numbers of the dice. And this sum we call the random number. Now at first glance this mapping just would give every element of omega a random number, but then you see that different tuples can be mapped to the same sum. So in this sense, every random number here, I and j, is associated to a set of tuples which have the same sum. So and then, so we have, in this way we can construct, for example, random numbers. So one advantage of having random numbers instead of subsets of omega is that we have a nice way to visualize all the possible probabilities in a simple function. Because since numbers can be ordered, and that's a difference to subsets. Subsets cannot be ordered, but numbers can be ordered from smaller to larger. This allows us to visualize the probabilities of all possible outcomes of an experiment. And this visualization, this plot, we call the distribution. So how would this work in this example of the sum of two dice, a throw of two dice? So we can make a plot, and here we plot our random numbers, and here we have the probability of these random numbers. So now let's see what possible random numbers can we have here. The sum of two dice, the smallest possibility that we have is the 2, if both dice have 1, and then we can have 3, 4, and so on. And we can go up to 12. 12 is the largest outcome that we can have as the sum of two dice. So that so even though the sample space has a size 36, we have only here 11 different random numbers. And now we can calculate the probabilities of all these numbers. And so what's the probability to have a 2? And you can easily see that there's only one possibility that you can have 2 if both the dice have, first dice is 1, second dice is 1. So here the probability is 1 over 36. In a similar way, we can have the event 12 only if both dice show 6. Again, there's only one possibility, 1 over 36, that's the probability. So the probability to have 3, okay, so we can have 3 if the first dice is 1, the second is 2, or the first is 2 and the second is 1. So here the probability is 2 over 36. Similar here also for 11, and then so on and so forth. You can see the probability to have 4 is this, probability to have 5, probability to have 6, probability to have 7, probability is 6 over 36. And so this is now the distribution. The distribution is nothing else than a graph of the probability of every random number. And so with one glance we can see the whole structure of all possible outcomes. Sometimes to see this even better, plot here a line in between to see better, for example, here the triangular shape, but this should not confuse us. The probabilities are associated only to the natural numbers here, to the random numbers, and not to the values in between. So that's the basic concept, what is a random number and what is the distribution of random numbers. So at this point we have to make a distinction in the case I showed you before, here we had a finite number of possible random numbers, and that's often the case. So we have only finite number of random numbers, or maybe infinite but countably many random numbers. So this would be the case A, where we say we have a discrete random number So by discrete, mean that we have a random number which can now have an index I, and this I runs from 1 to 3 and so on, maybe to infinite or in a finite set, but it's countable. So the distribution, in this case, as we have seen, we have here the possible xi's. We have the probabilities of these xi's. Sometimes we also say just pi, meaning the probability of the ith random number. And we can visualize the distribution by a graph. Of these numbers. And sometimes, as I told you, we connect the lines to have a better idea what this graph will be. So that's the first case of random numbers that we can have. But often we don't have discrete random numbers. We can also have random numbers which are continuous. Continuous random number, this x will be a real number, and then we have really a function p of x. Sometimes, we are just by the index, if we have pi or px, you see if it's a continuous or discrete distribution. And now with the continuous random numbers, there's one thing we have to keep in mind. There is some additional subtlety. So we can of course also visualize the distribution. Here x, p of x, and then we have some function which might look like this. And now we have a continuous function. So we usually assume that this function p is smooth, it's continuous, and has a continuous derivative typically. But what we want to normalize our probabilities. Maybe let's write this down directly here. So what do we mean by normalization? We know that the sum of all possible random numbers must be 1. The sum over all random numbers in the discrete case. Why should it be like this? Yeah, because all events are mapped to a random number. We know the probability of the whole sample space is 1, so the sum over all random numbers should be 1. Yeah? Because one of the events should appear. So how can we normalize such a function in a continuous case? It should be clear that then this sum goes over to an integral. So let's maybe directly write down this integral. In the continuous case, we have then here an integral of our function p of x dx should be 1, and we here integrate over either the interval in which the x is defined. So x might be either in a finite interval, or it might be over the whole real numbers. from minus infinity to plus infinity. So what in the case of a discrete distribution is a sum goes to an integral in the continuous distribution. And but you see here we sum probabilities, and here in the integral we also sum probabilities, but the probability is not this p of x, but p of x times dx. So what does this mean? If we have a certain value x here, and we look at this value p of x, then this p of x is not directly a probability. In order to get a probability, we need to have here a finite interval. We go from x to x plus dx, a small increment, and then we look at the rectangle under our distribution, and the size of this rectangle, so this p of x dx, this is the probability to have a random number in this interval. So p of x dx is the probability for random number in this interval between x and x plus dx. So you have always to keep this in mind. In the discrete case, the values of our distribution directly are probabilities. In the continuous case, we have a probability density. So actually we have to deal here with a density. And only integrals over densities are probabilities. So we call this here the probability density function. And we abbreviate it by PDF, the probability density function. So in the whole of the theory that follows, we always have to keep in mind and to be aware, do we have the discrete case, the continuous case. In one case we always have sums, in the other we have integrals, and in the continuous we have just a density. Now sometimes then in the lecture I will be sloppy and I will not really make a difference, and I just speak about a PDF. Even though maybe strictly we would have discrete random numbers, and I assume that always from the context it will be clear if we have this or this case, you know. And so usually for me PDF is just this probability density. In most cases when we get here such a plot, and this plot, the shape of this plot gives us some information about the stochastic process, or the process, or the experiment that we're dealing with. These functions are not arbitrary, so these functions that we have are normalized. And here, I mean, this piece must of course be positive. So in the discrete case, pi's are between 0 and 1. In the continuous case, the p of x must be positive, but they're not necessarily smaller than 1. In principle, we could have here a large peak if it's just small, because the important thing is that the whole normalization, the whole integral is normalized to 1. At one particular point, this p of x might be larger than 1. So that's also a difference between the discrete and the continuous case. In the following, we will see quite a number of different distributions and we'll learn their properties. But before we do this, there is maybe one thing I want to introduce here, and this is the cumulative density function. CDF. The cumulative density is an alternative way to show the distribution here, and it has the advantage that we really have probabilities. I mean, the problem here with this density is that the value, this p of x at the position x, cannot really be interpreted because it's not a probability per itself. We always need to integrate. So if you want to prove some theorems about such functions, this is a bit problematic. And so we can introduce this function. You use always this notation, p smaller of x, and this is then an integral. We integrate our distribution, p of x prime dx prime from minus infinity to x. And since this is here an integral over our probability density, this p smaller is really a probability. We can really interpret this value here as the probability for a random number that is smaller than x. You can of course construct this also in the discrete case, where we would say p smaller of the position xi. This is then the sum of probabilities j, so that j is smaller than I. Analogous definition in the discrete case. And now, when you look in the literature of probability theory or stochastic processes, it's that in the physics literature or literature written by physicists, they use more the probability density function, this PDF, because the shape of the PDF is typically more characteristic for the distribution. You can read more information in the PDF, versus while the CDFs, they more or less always look the same. We will see they're just increasing functions. On the other hand, if we have literature written by mathematicians, they prefer more the cumulative density, because that's a real probability, everything is better defined, and it's more nice to make proofs and calculate things. And this means now, depending what kind of literature you're reading, when people speak just about the probability, they might mean the PDF or they might mean the CDF, depending from which background they're coming. And so, for example, this cumulative density function, sometimes it's called the distribution function. In particular in the math literature, because this literature, this function here is the fundamental quantity, that's the distribution function. Whereas in the physics literature, this very often we call it the, say, density function of a probability distribution, and then we always mean this PDF. Okay? So there is a possibility of confusion, in particular if you change literature. In this lecture, I will try to use consistently, if I just have p of x, I mean the PDF, and when I write this p smaller of x, then I mean the cumulative distribution. And when I, since I come more from the physics background, when I just speak about a distribution, I will always mean the density. So that was now some definitions. So in the next video we will see some examples for distributions. Okay, thanks.